All right, so for this gearbox here, someone was asking, so I'll discuss there are multiple efficiencies inside of this particular problem. You can see right here where it says cascaded equipment that you could have multiple parts, right? So here's part of a system. In the first problem, in this problem, that's the motor, whereas this one is the gearbox, and there's not a third one in the problem, but you have an overall efficiency. Then you have an efficiency of one piece of equipment right here, an efficiency of another piece of equipment. And so that's what we're doing in this problem is we're using kind of that idea that I said of the engineering format of what is given and what are we being asked to find. And so in this one, we're kind of starting with this idea that we have 110 watt is coming out at the very end. That's the power coming out of the entire system. So in that cascading equipment picture, put it with two things like that inside of it. And so the first one, this efficiency 2, and that's the Greek symbol eta, ETA, right? And its efficiency is 75%. And so the first part, A, is asking what is the horsepower of the motor? Well, that one, we can basically just, the horsepower output of the motor, I'll say P motor out, because this is what's coming out of, and I guess it's poorly worded because the overall thing is the motor. So we'll call it of the system. And if that confused you, I'm sorry. But it's essentially going to be the output of the system. And so it's saying just what is the horsepower output? And this would be more for real life purposes. If I had an electric motor that needed to actually spin something, think of like a power drill, right? I have an electric power coming out of my wall, going into my motor, and then the output power that I need to use. So you have an input coming into the motor and an output coming out of the electric drill that's going to actually turn a screw. Right, so this P out, it's not going to actually help us solve anything. I'm doing the railroad tracks here to convert it into horsepower, 1 horsepower, 746 watts. But it is a good reminder that that conversion is always there. And that 1 horsepower to 746, that is on the equation sheet. There's a section that says motor, and it is there. So that's 1.475 horsepower. So that's what's actually usable for this motor. Or think of like an elevator, uses electric power and it's going to turn something. That's what the usable horsepower of it is. So the efficiency of the motor now, and it's kind of like there's this in-between spot between eta 1 and eta 2, between the motor and the gearbox. And so if I'm solving for eta 1, there's this P in the middle that we could call, say, P prime. And that P prime is, don't want that. It didn't like my drawing there. It turned into a triangle. P1 or P prime in the Pn. So that's what's coming out right here in between. P prime is that in between the motor and the gearbox. And so what we can solve for is, no. We can solve for the P prime by using P out over eta 2. And the reason why is because we know that that efficiency of eta 2 is 75%. So the P out is 1100 watts divided by 0.75, and that gives us 1447 watts. So now we can plug that in here to eta 1, 1447, P in 1600, and we get 91.7%. So that's eta 1. So now there's 2 ways that you could get the eta total, right? You could take the total system and say that the total system has 1100 watts coming out and 1600 watts coming in, P out over P in, and we would get 68.8%. The other way you could do it is you could multiply those efficiencies, eta 1 times eta 2. And so if eta 1 is 91.7%, multiply that by 75%. If you're doing that in the calculator, remember that would be like 0.91 times 0.75. That's what the percent means. And then that comes out to 68.8%. So there's example 13.